Thank you for the invite. What I'll be presenting today is part of my PhD project at Oklahoma State University. And I work with quite a number of collaborators on this. So the results I will be showing have been published in Frontiers in Earth Sciences earlier this year. And just to start, I would just go through like a brief background of the studies and models we used in our study. When it comes to rifting and normal faulting, it has been suggested that usually starts at isolated fault segments. So it goes from the first stage to the second stage. So as the strain localizes, the fault becomes larger in terms of length and displacement, and there's formation of grabens and half grabens. So that when you plot the fault displacement against time, over time you see that linear increase in fault displacement. And the models to the right are just to remind us of the two end members of the rift growth models. We have the tip propagation and the constant length model. And the difference is just for tip propagation, it is believed that when normal faults grow, there is this simultaneous increase in length and displacement of the fault. But constant length is the fault is formed almost instantaneously, then it only grows by displacement accrual. Then there's the intermediate model in between, where there's linkage of segments or bisolated segments. And there have been different approaches to study how this normal faults, how it grows. There have been field observations, experimental approaches. Then there's this recent study by Colley et al., where they used thermochronology. So they dated different along strike of the fault. They had profiles for thermochronology, and they dated it to test each of these models. And based on all these studies, there is this empirical relationship that exists between the maximum displacement and the length, where G max is the maximum displacement and L is the length. C and N are constants, like different factors that can make this vary. But in 2019, there's also this hybrid fault growth model that tries to bring together these two end members. And they propose that the lifespan of the fault, the first 20 to 30% of the fault lifespan grows by propagating tip model. Then over time, it grows by constant length model, which is just accrual of displacement until the fault dies off. But there can be a series of variations in how normal faults growth patterns occur along the rift system, because there could be variations in the type of rift systems that we have to. So is the rift system, is it magma poor, magma, or is it assisted by magma intrusions? Just like what I will be showing today, this is just showing the difference between the western branch of the East African rift system and the eastern branch. So the western branch is believed to be magma poor, and the eastern branch of the East African rift system is assisted by magma intrusions. So all these, when you put them into account, it affects the kind of fault growth patterns that we see. So to jump into my study area, it's in the East African rift system. And we have the western branch of the East African rift system right here, and we have the eastern branch. So the Malawi Rift in the rectangle, in the white rectangle, is part of the western branch of the East African rift system. And it's believed to be magma poor, so it's just crustal extension. So the figure I have in the middle is showing the structural map of the entire length of the Malawi Rift. And here I'm highlighting the major border faults across the rift. So we have from the north, we have the Livingstone Fault, the central basin, we have the Usisia Fault, and the south basin border fault. And across the entire length of Lake Malawi, which is in blue, there are seismic profiles. So most of the faults you have here, the Livingstone, the Usisia fault, and the South Basin border faults, have been studied extensively because there is seismic profiles. They've been able to estimate the throw and the displacement. But just south of the lake, there isn't too much data down there. So most of these faults have not been properly studied. And the Belila and Takataka faults, this is the faults I will be focusing on today. It has been believed it's hosted a magnitude 6.2 earthquake. So it's quite important and massive for it to not have an estimate of the amount of throw or displacement on this fault. And this is just a close-up of the structural pattern along the fault zone. So you have the Belila and Takataka fault, and just behind it we have the Chirogwe fault, and we have the Malombe Basin and the Malombe fault just east of it. So for our study, we concentrated on this fault. There was a previous study that looked at the scarp of the fault, but what they did was they just looked at the surface expression of the fault. But recently, the fault has been suggested to be the length of the fault is suggested to be seismogenic. That means it cuts through the entire crust. So we believe there is more to this fault than just the surface expression, which is just a few meters. So we decided to incorporate the surface aspect of the fault and the subsurface aspect. So for this study, we used 3 different methods. We did profiles based on digital elevation models. Then we also incorporated aeromagnetic data to look at the subsurface part of the fault. Then we acquired electrical resistivity just across the fault to look at the variations across the fault zone. And I would like to mention that this area, the geology is just basically on the footwall, we have mostly Precambrian basement rocks, just gneisses. And on the footwall, we have Cenozoic sedimentary deposits. So to incorporate our method, this is just a schematic diagram to show what we measured and how we measured it. Right here, we had to measure the throw on the surface. Then we also had to measure the throw in the subsurface. And for the surface component of our study, we measured scarp height, which is H. Then we measured the local footwall hosting that scarp height, which is our H prime. Then using aeromagnetic data, we estimated the depth to the magnetic basement, which we assume is the throw. So that would be the amount of throw the amount of subsidence that have happened based on the top of the basement. So combining these 2 data sets, we were able to estimate the minimum throw we think has occurred on this fault. Then, so that's just to look at the variations and patterns along the fault. We also wanted to see image of the fault itself, the orientation of the fault, the dip, and so on. So we had to collect electrical resistivity. So we had profiles perpendicular to the fault for the imaging. And in this figure, we are showing how the river cuts into the mountain front. This is important because we used it in our interpretation. And the figures these are figures from the field showing how the profiles were taken. So we have the resistivity line laid just perpendicular to the fault, and what we estimated as our fault scarp, the footwall, and the hanging wall. So based on all that, I will just show some of our results now.
You're at the 10-minute mark now.
All right. So we generated a length against throw. We generated, so on the horizontal axis, we have the length of the fault, which goes from the northwest to the southeast. And in brown, we have the scarp height. In green, we have the local footwall height. And based on that, we were able to identify how segmented the fault is. So our categorization of segmentation is based on the points between two minimas. So where we have minimum amount of throw, that's where we believe to be tips of each segment. And we have, based on that, we categorized it into scarp segment 1 to scarp segment 5. So this is from our study. This is from the previous study that I mentioned that looked just on, they based their study just on the surface aspect of the fault. So incorporating the aeromagnetic data, we used the total magnetic intensity to generate the depth to magnetic basement, which shows the variation of the depot centers across the fault. And based on this, we were able to extract the depth to the magnetic basement just perpendicular to the fault across the entire length of the fault. And from that, we were able to generate another throw against length plot. So which is, we have the length of the fault on the horizontal axis, and in blue, we have the depth to magnetic basement. Then the cumulative minimum throw is just the addition of the subsurface and the surface component. And we were able to say that there's 3 major composite segments, which tells us that there's the surface component only shows the most recent activity along the fault. So when we need to look at the long-term accrual of displacement, there's need for incorporation of the subsurface part of the fault. Then we looked at the electrical resistivity profiles, and from that we were able to estimate the depth of the fault, which are between 70 and 75 degrees. And we made our interpretations of the electrical stratigraphy based on the geology of the area. So it's mostly overlain by alluvial sediments from the rivers cutting through the mountain fronts. Then we have that underlain by lake sediments. Then we have the weathered basement and the fresh basement just below that. We were also able to estimate like minimum amount of throws from our electrical resistivity. And I'm trying to show where each of these profiles are along the strike of the fault. So there tends to be variations in this, in the amount of throw and the depth of the fault as we go along strike. So where the profile is close to the center of the fault segment, we tend to see more displacement along that front than, so this third profile is right along where we have a relay zone, just connection between two fault segments. And it shows that's where we had, which is consistent with our results, where we had minimum amount of throw. I would also like to mention that this electrical profile 3 was not acquired perfectly perpendicular to the fault. That's why there's some sort of low angle faulting. And we did not use this to estimate the depth of the fault. This is just the last profile, which is on this last segment. And it also shows a 70-degree depth of the fault. So based on all this, now we have the throw of the fault, we have the depth of the fault. We can actually estimate the amount of displacement on the fault. So we decided to plot that using the fault against maximum displacement plot. This is a log scale. So we were able to determine the amount of displacement to be in the range of 580 meters to about 800 meters. And this is where it plots. So when we compare that to other faults along the Malawi Rift, it shows a huge difference, even though their lengths are similar. So this is the basis for our interpretation of this fault being under-displaced. And someone might think, oh, it might just be younger than these other faults, but there have been recent studies that suggest faulting started in this part of the rift almost at the same time as what we have along the Bilila and Takataka faults. And to conclude my talk today is, I would like to just, this are the takeaway from our publication. We were able to show that the Bilila and Takataka fault is one of the longest faults, as you can see from this global data set. And it showed this alternating phase of growth, lengthening, and accrual displacement of these fault segments. And from our observation of it being under-displaced, we suggest there's potential for significant seismic hazards over time, because there's still room for this fault to accrue a lot of displacement. And this project was funded by NSF. The acquisition of some of the data was funded by NSF. Then I would also like to acknowledge the efforts of everyone that helped acquire this data in the field in Malawi. And I would also like to thank my collaborators and everyone, and thank you for listening. Happy to take questions now.
Thank you so much, Wanda. This is a wonderful multidisciplinary study. My favorites. If anybody's got any questions, you can put them in the chat or you can put your hand up. While we're waiting, you showed two different estimations of the fault segmentation, where you had the composite segments versus just the regular 5 segments. How well do those correlate in terms of the boundaries between the composites or the separate segments?
You're talking about this, right?
Yeah.
Yeah. For the southern part, it corresponds really well. So where we have this minimum amount of displacement as the relay zone, it corresponds really well with where we have this. But in the northern part, there's a slight deviation from what we have for the northern part. And I guess this is because the results also suggest that there have been, so the connection we have for the segments here, it's suggesting that it's more recent than what we have in the north, because the magnitude of the minimal here is smaller than what we have here. The more the time that has passed, the lesser it is to actually identify if there was a segment there before or not. So we just believe the north coalesced earlier than the southern part of the fault.
Okay, that makes sense.
Yeah.
Thank you. There's also a question from Derek.
Oh, thanks. Great talk. Very interesting. Yeah. The question is, what are sort of the uncertainties on your estimated depth to magnetic basement, and sort of hence the fault throw?
Oh, yeah, that's a very good question. I was actually going to mention that. So the aeromagnetic data that we used has a 20% uncertainty, and these are the error bars, just to show that 20% uncertainty. Yeah.
So I guess even if you take the maximum displacement, they're still under displaced, I guess.
Yes, yes. And we actually, so when on the estimate that we have here, you can see there's a slight error bar there too. So we incorporated the errors and the variation in the amount of dip to estimate. So that's why it goes from like 580 meters to 867 meters.